start with section 2.13a, exponential logarithmic equations and inequalities, and I'm going to try and speed solve these. It says you can use your calculator, and so here we go. I'm going to zoom into each problem as I run through them. So I've got a logarithm right here. I can see it's a logarithmic equation. I've got to check its domain. I just want to make sure what kind of answers I can get before I solve it and get carried away. So I know my answers have to be x's that are greater than 2.5. Now I'll start to attack it. The logarithm's alone here, so I'm just going to switch to exponential form. And you can see my base is 7, my exponent 2. This is just a linear equation because 7 squared is just 49. I add my 5 and divide by 2. There we go. X is 27. I don't need a calculator to figure that out. All right, on to problem number 2. Let's see here. Now this one is exponential, so I don't have to worry about my domain. X can be any number, fractions, decimals, irrationals, doesn't matter at all. So I just need to get the term, this 2 to the 3x. It's actually the factor of this term. But I first want to get this term alone, then I'll get that individual factor alone, the factor with x in it. All right, so first I'm going to get rid of the 4 here, go down and do my additions, and I've got 5 times 2 to the 3x. That little parentheses around the 2 to the 3x is emphasizing the fact that you cannot multiply those two numbers together. Now we can divide by our 5. Talking here, not watching my math, that's a 10. So now that I have that alone, one thing I could do is, like, this is a base 2. I could hope to write this as a 2. Like if this was an 8, I could write 8 as a 2 cubed, and I could equate my exponents. But I don't have that option here because 10 is not a power of 2. And so instead what I'm going to do is I'm going to log base 2 both sides. Or I can think of it as changing to exponential form. Now I like to just log both sides. So I'm going to go log base 2 of this side, and I'll log base 2 this side. Now over here, this is just 3x. Log base 2 of 2 is 1, so this just, that 3x pops out front. We've done this a number of times. So 3x equals log base 2 of 10. And so x is divided by 3. Log base 2 of 10 over 3. Or 1/3 of the log base 2 of 10. Okay, this might be something they might write it as in the AP classroom, a little bit more formal. Let's get the decimal approximation. So log base 2 of 10, I would probably calculate that first. I can go to math. I can choose my log base. I'll put a 2 in, then I can put my 10 in, like so. And that would give me that decimal. Then I have to take it times 1/3 or divide it by 3. It does the same thing. So you can do it like that. Now, I usually do this stuff, though, by using the change of base formula. So my math would probably look like this. I'm going to put my 1/3 in there first. I'll say 1/3 times, and I'll write just log 10, log the argument, divided by log 2, the log of the original base. And you'll see we get the exact same number that we got before. But x is then to the 1000th 107. Will be our decimal approximation. Alright, 1 and 2 done. Let's jump to number 3. Alright, I got some logarithms. So let's check out some domains. X minus 3 has got to be greater than 0, so x is greater than 3. X minus 4 has to be greater than 0, so x is greater than 4. So x has to be greater than 4. Because if you're greater than 4, you'll also be greater than 3. So I've got logarithms all over the place. What I'm going to do is, when I have a situation like that, is try to condense it down to a log equal to a log. Equals log 5 like this. Because now that log equals log, I can say, well, these arguments then must be equal to each other. And that allows me to just drop my logarithms and just go, hey, x minus 3, oops, got my highlighter chosen there, x minus 3 over x minus 4. You must be equal to 5. Let's see here. To solve this guy, not super easy. Notice though I've got x minus 4 is now in my denominator. So x can't equal 4. I'd have to toss out that, but x is already greater than 4. So we're okay there. I'll multiply both sides times x minus 4. I want to get rid of this fraction here. This cancels, so I get x minus 3 equals 5x minus 20. I'll get all my x's on one side. Maybe I'll subtract the x there, and I'll get my 20 on the other side. So that gives me 17 equals 4x, so divide by 4. 17 over 4. I don't think, that's going to give us, 4.25. Okay, so there's a decimal approximation, but it's not an approximation. That is both exact answers. So there's number 3 for us. These are all very checkable. In fact, I'm going to check that one. I'm not super confident in my answer just because I've been talking the whole time and trying to work out some software. So I'll have to plug in the 4.25. And I'm just typing in the equation, replacing the x. It's nice and base 10, so it's really easy. So here's the left side of the equation, 0.69, and then I'll take the log of 5 and compare it, and holy cow, yep, those two are equal. There's another way to test something like this. I want to show you this. I often forget about it. So I'm going to scroll back up here and grab this equation right here. And above the math button, you can see it right there above the math button on the calculator. Is the word test. And you go second test. And you say, hey, do you equal log 5? So in that case, you ask, hey, does the left side equal the right side? And this either gives you a 0 or a 1 for an answer. 0 is false and 1 is true. And you can see we get a 1, so it's tested it. Said, yep, that's a true statement. All right, now on to problem number 4. Let's see here. Another exponential equation. You can see the x is in the exponent spot up there. So I want to get that exponent factor alone. So I'm going to multiply both sides by 2 here. So now it's just e to the x minus 4 equals 28. And then I'll natural log both sides. Use the base logarithm of the base exponential. My base is e, so I use a base e logarithm. And this just becomes x minus 4 equal to the ln of 28, or the natural log of 28. So it is 4. Well, I'd probably write it this way, natural log 28 plus 4, but you gotta be careful. You just want to make sure you know it's natural log of 28 and then add 4. Lots of times you'll see them write it with the 4 in front for that particular reason. Just say, hey, I want to add 4 to the natural log of 28. Okay, let's get a decimal approximation. 4 plus natural log 28 equals about 7.332. We get our decimal approximation. Number 5, let's see, logarithms, let's check some domains. 2x minus 4 has to be greater than 0, so 2x is greater than 4, so x has to be greater than 2. 5x plus 15 greater than 0, 5x greater than negative 15, x has to be greater than negative 3, so our answers have to be greater than negative 2. That's our domain. Got a couple of logarithms, so we're going to squish them into one. Changing it to a multiplication. And now that I have log equal to log, I can negate the logs, essentially. So 5 times 2x minus 4, I could have distributed right there, but I didn't yet, equals 5x plus 15. In fact, I'm not going to. Instead, I'm going to choose to divide both sides by 5. I get 2x minus 4 equals, when I divide by 5, I get x plus 3. Subtract my x from the left, add my 4 to the right, I get x is 7. And that is in my domain, so I am good. Problem number 6. Here we go. Let's see, x plus 9 has to be greater than 0, so x is greater than negative 9 is my domain. Let's see here. I'm going to take this 12, move him to the other side. There we go. So now I got negative log base 2 of x plus 9. You see that negative out front. We got a couple ways to deal with it. 14 minus 12 is 2. I'm just going to take him to the other side. I'll just divide or multiply by -1. Either way, it just makes it a -2. And now I'll switch to exponential. My argument is equal to my base to the -2 power. Let's see here, so x plus 9 equals, negative exponent, so I want to reciprocal it. So x plus 9 is equal to 1/4, or x equals, subtract 9, giving me -8 3/4, or -8.7. I think that's 1, 2, 3, 4, 5, 6, and we just got 7 here. Calculator, solve the equation with a graphing calculator, round to the nearest thousand. So solve with a graphing calculator, we can just graph the left side, so we could do it this way. Okay, I'm going to graph this one, so I'll make y1 equal to 4/5 of 4 to the 2x minus 5 minus 4. I'll make y2 a 20, and I'll just find out where they equal. So y1, I'll go 4 divided by 5, parentheses, 4 raised to the 2x minus 5, arrow over, in parentheses, minus 4. So there's the graph of the exponential, and when does it equal 20? And we'll just find out where they intersect. So I'll do zoom standard here. Well, you can see it only goes up to 10, so I'm going to have to, I'll do it the way you guys would, so I'll do zoom standard like this. I want it to go up to at least to 20, because that's where my y2 is. So I'm going to change my window here, and I'll set my y max to 25. And so my graph will be pretty much the same, except now I'll get to see this point up here where they intersect each other. And I can see the y value is 20, and I can read the x value at that point as well. Looks like get that point of intersection. When y is 20, x is 3.726. So x equals 3.72, and we'll round that to 7. There we go. We just solved it with our graphing calculator. You could do that with all of these. Okay, but we got to know those math rules so we can do expansions and contractions and do whatever they ask. All right, that is it for this section.